Hi friends, today we are going to see the stereochemistry of cyclohexane. So in this we are going to see Baeyer-strain theory. If you are visiting this channel first time, please subscribe the channel. So let's go directly to the stereochemistry of cyclohexane. So you should know something about the cycloalkanes. What are the cycloalkanes? As cyclohexane is the example of cycloalkane. So cycloalkanes are saturated hydrocarbons in which a ring is present and that ring is made up of carbon atoms. Usually in open chain molecules, carbon-carbon bonds have freedom of rotation. But in case of the ring structure, cyclic structure, so ring possesses a rigidity and therefore cyclic molecules have some sort of torsional strain and non-bonded repulsions. And hence freedom of rotation is restricted, and that freedom of rotation is rises the different types of stereochemical isomers present in cycloalkanes. These are some examples of cycloalkanes. So this is the cyclopropane, as 3 members are present there, 4 members cyclobutane, 5 members cyclopentane, so 6, 7 and 8, that's the cyclohexane, cycloheptane and cyclooctane respectively. Now related to this compounds, Baeyer's has proposed one theory, that's the Baeyer-strain theory. So this Baeyer-strain theory is related to the stability of cyclic compounds. So what is Baeyer-strain theory? So Baeyer assumed that all ring systems are planar geometric polygons. So like this, just we have seen that. See here. So all these are geometric polygons. It looks like a geometric polygons, and hence Baeyer also assumed that the all ring systems are planar geometric polygons. The cyclopropane and cyclobutane ring systems shows deviation in normal tetrahedral bond angle, which produces strain in the ring. So usually we know that what is the normal tetrahedral bond angle? It's a 109.5. But in case of the cyclopropane and cyclobutane, if you see here, so that internal angle, if you see, it's a 60, here it's a 90. So it's not a normal tetrahedral bond angle, that's the 109.5. And due to that, it possesses some sort of angle strain. So what is the angle strain? So angle strain is defined as the difference between the normal tetrahedral bond angle and the internal angle of cycloalkane. So here it is. This is the internal angle. And normal tetrahedral bond angle is 109.5. So you have to just do the subtraction. Okay, that we'll see afterwards. So what happens due to this angle strain? So this angle strain will make the molecule unstable as compared to the molecules which having a normal tetrahedral bond angle. So molecule becomes deformed. This is also known as a deformation of molecule. Okay. So cyclopropane and cyclobutane will easily undergo ring opening reactions because they are highly unstable, and hence they will show the ring opening reactions. And the large ring systems usually involves negative strain, and hence they are unstable, in fact very unstable, and do not exist. So these are the assumptions of Baeyer's, and this is known as a Baeyer-strain theory. So here it is, all compounds that we have taken here, so cyclopropane to cyclooctane, and their internal angle is shown here. So right from 60, the 90, 108, 120, 128.6 and 135 degree. Now, as Baeyer assumed that all these cyclic compounds, these are the geometric polygons. So depending on the internal angle, we can calculate the angle strain. So angle strain is calculated by this formula. So angle strain is equal to half of tetrahedral bond angle minus internal angle. Now, why this half is taken here? Because the strain is spread over the two bonds. Here it is. So that particular two bonds are there usually, and hence that strain is spread over the two bonds, and hence it is taken here half. Now how we can calculate that? Let's see here. If you have a cyclopropane, so ring size is 3, so 3 members are present there. So internal angle 60 degree. So just we can calculate this by this formula, and we will get that 24 degree and 44 minutes. Similarly for cyclobutane, 4 membered ring, so internal angle is 90, and you are getting this angle strain 9 degree and 44 minutes. So as internal angle is increases here, if you see, so that angle strain is decreasing now. So for cyclopentane, it's 0 degree and 44 minutes. For cyclohexane, it's 5 degree and 16 minutes. Here it's given it's a negative. Actually, the angle strain is not negative. It's just given due to that because so for cyclopentane, it is 0 degree and 44 minutes. For cyclohexane, it's a 5 degree and 16 minutes. For cycloheptane, it's minus or 9 degree and 30. So for cyclopentane, it is 0 degree and 44 minutes. For cyclohexane, it's a 5 degree and 16 minutes. For cycloheptane, it's minus or 9 degree and 33 minutes. So usually it is taken as a modulus. Angle strain is taken as a positive value. For cyclooctane, it is 12 degree and 46. So by analyzing this table, we can say, if you see here, cyclopentane should be the most stable as compared to the remaining compounds, while cyclohexane, if you are comparing with the cyclopentane, so cyclopentane should be more stable as compared to cyclohexane, but actual different thing is there that we have to see afterwards. So this is about the angle. Okay, now why Bayer strain theory failed? So because Bayer made first false assumption that all ring compounds were flat. So Bayer's strain theory cannot be applied to rings larger than 4 members. For example, if you are taking here, this is the regular hexagon, its internal angle is 120, which is the deviated from normal tetrahedral bond angle, that is 109.5. But this cyclohexane ring is folded in such a way so that normal tetrahedral bond angle is maintained to 109.5. This is known as a puckered ring structure of cyclohexane. So if normal tetrahedral bond angle is maintained, then obviously that ring is strain free. There is no any angle strain, and if no angle strain is there, that is highly stable compound, and that's why Bayer's strain theories failed here. That first false assumption that all ring compounds were flat, but actually as the ring size increases, that ring becomes folded, so it becomes a puckered ring. Okay, now let's go for the second assumption. So what's the second assumption here? So Bayer proposed that larger rings are unstable and therefore they are difficult to synthesize. But why larger rings are difficult to synthesize? Let's see the reason. So for any ring closing or cycle formation, two ends of chain, this is the chain, so these two ends should come close, then and then ring will form. So this is known as a ring closing. And second thing happens when you're doing that ring closing, as these molecules are the larger, so there is a possibility of chain lengthening. So instead of coming these two ends come close, the one end of one molecule and the other end of other molecule, they come close to each other easily, they form a bond and chain lengthening takes place. So instead of ring closing, chain lengthening probabilities increases, and therefore larger rings are difficult to synthesize. So remember that this is the important thing why Baeyer-Strain theory failed here. Okay. Okay. So thank you very much for watching this video. Please subscribe my channel Chemistry Basics and press the bell icon button so you'll get the notification of the next video. And if you like this video, please share and comment in the comment box. Thank you very much.